Has anybody here ever used actually used one of the original Macintoshes from 1984? Like that? You remember the little sliding number 1516 puzzle? That you can see a part of it. Interesting fact. I don't know. It was almost dropped from the thing. They had the guy who had written it. The people in charge came to him and said, look, we want to include this thing. It's kind of nice, but some people think you make it look rinky-dinky, and it's 6 kilobytes, and this whole thing has to fit on a floppy disk and still leave room for the people's files and everything. We're thinking maybe we need to make room. And I said, well, look, the only reason it's so big is because I wrote it in Pascal as a demonstration of how to write this kind of code. It's the Pascal runtime taking all the space. Just let me rewrite an assembler, and it'll be much smaller. And they went back and forth, and they said, okay, look, if you can get it down to 600 bytes, we'll keep it in. But the manual's going to the printer on Monday, so gonna have to be done over the weekend. So he went over the weekend, rewrote the whole thing in assembly, got it down to 600 bytes, and it went in. When I read that story, I thought to myself, God, when is the last time I saw an executable that was 600 bytes? And then I thought to myself, wait, when's the last time I saw an executable that was 6K? I mean, we've kind of gotten used to the fact that we don't even think about these things anymore, but 6K is almost nothing now. So I tried sitting down, writing a program, just the simplest one I could write. We've all seen this. I'm returning a non-zero value just so I can tell that the program actually does do something, since it's not going to print anything out. And we give it to GCC and try building it. And sure enough, exit code is 42. 8K. That's really quite bigger than I thought it was going to be. So what are some easy things that we can do to smallify it? Obvious ones. Anyone?
Strip the executable.
Strip the executable. That's what it's there for. Verify that it still works. Yes. 6K. Any other obvious ideas? How about switching to a 32-bit executable? Even though we're all using 64-bit operating systems nowadays, we still maintain backwards compatibility with all 32-bit executables. This should make it a little bit smaller. Like that. Oh, and of course, I can strip it. Here's a quick saver. If you just pass -S, that'll get passed on the linker and automatically strip it for you. Down to 5K. So now at least we're under 6 kilobytes. So, what's the next step? How do we make this smaller?
Ask GCC to optimize for size.
Yeah, optimization. I believe GCC has sort of unofficially stated that optimizations up to level 2 should never increase the size of the executable. After that, it starts doing more exploratory ones. Oh, that's a good point. I forgot about that, yes. That's even better. Yep. No difference. Well, there's only so much optimization you can do with a one-line program. So I think what we have to do here at this point is switch to assembly. There's no help for it. Hopefully then we can bypass the C runtime library, much as they did, and get something better. So let's clean this up, and this might seem a little scary for those of you who are not familiar with assembly. I encourage you to just kind of muddle through as best as you can, and you'll be able to pick up enough, I think, to continue on. And I just want to say that all of you people here who never knew a time before the Intel syntax, you just don't know how lucky you are. Oh my God. Okay, so how we return from a function is that we store the value in the accumulator, EAX. So we do that, and we return. And there's our code. The simplest assembly language program I've written in a long time. Did it work? It works. No difference. The problem is that we haven't actually stopped using the C runtime. We are still using the main interface, and so GCC is still giving us the entire C runtime. The fact we've written in assembly makes absolutely no difference at all. So in order to get around this, we need to stop using main. So if we don't use main, how do we get started? Does anybody know? There is a special symbol called _start. And GCC actually provides this for us by default. It provides a function that called underscore start that simply just sets up the stack and calls main. So if we use underscore start instead, then we can do this. Multiple definitions of start because we are still getting the C runtime start. And so now we have 2 starts and no main. Fortunately, GCC, they care about us. They thought about you might want to do weird things like this. And they gave us a command line argument called no start files, which tells it not to link in its own start. And here we go. And now we have an executable that segfaults. Why did it segfault? Well, if you dive into this a little bit more, you'll find out that it segfaulted at the return. If you look at what's on the stack, the return value that it's trying to return to is the number 1, which is, I don't know about you, but most addresses, I'm not used to having zeros, that many zeros on an address. The problem is that when underscore start is invoked, it owns that process. Nothing called it that's inside that process. There's nothing above your program at that point. If you want to, end the program, you're responsible for cleaning up that process. How does that happen? Anyone know? What's that? Exit. That's what it's there for. We have to call exit. So instead of returning from a function, now we need to call exit. So to call it, we will push our argument onto the stack, and then we use the call instruction. Now, there's the issue there whether we want exit or underscore exit. As a general rule, I find that if you have bypassed the startup code, it's better to bypass the shutdown code. Underscore exit is just a thin wrapper around the system call. So it varies from versions of Linux and libc. But this, I believe, ta-da! It worked. And now the size, it's about 100 bytes smaller. Not quite as much as I was expecting, but still, it is definitely an improvement. So maybe it's time to actually look at this file. So readelf, object dump is more the standard program, but readelf is a little more specific to ELF files and will give us a clear idea of what's going on. And as you can see, this file is still full of stuff. We don't have time to go into all the stuff, but most of it has to do with dynamic linking. Dynamic linking is a very complicated subject. It involves a whole bunch of stuff. There are string tables, symbol tables, global offset tables, procedure linkage tables, hash tables. There's a huge amount of stuff in there, and it's kind of frustrating because all we're trying to do is just call exit. And we need all this machinery just so we can leave. So how do we do that without involving libc? Is it possible? Anyone know?
Yes.
It is. That's right. Thank you. The issue is that we have to make the system call manually ourselves. And so to do that, we need to know how to make a system call. How to make a system call under Linux, I will tell you. What we would need to do is, you may recall from the MS-DOS days, if you ever played around with that stuff, that the interrupts are how we switch between the user land into kernel land. Linux routes all of its system calls through a single interrupt, and that is 80 hexadecimal. That's for 32-bit Linux, by the way. 64-bit Linux, they actually, with a 64-bit chip, they actually introduced a syscall instruction, and that's what it uses. But a lot of the basic ideas are the same. The syscall, trying to be as flexible as possible, does not require you to have a valid stack. Everything is done through registers. The accumulator register is supposed to be initialized with a number that indicates which system call you want. Exit happens to be system call number 1. And then they all go down from there using small integers. After exit is fork, read, write, open, close, etc. All the kinds of stuff that you would expect to have. Then the arguments to your system call are then simply stored in successive registers from there. EBX is the first register. So for a function that takes one argument, we're going to be using EBX. Initialize it with 42. And normally when a system call returns, the return code is in the accumulator. It will be negative if an error occurred. Otherwise, it'll just be the return value. Since we don't expect this to return, we don't really care. So ta-da! We have run a program that doesn't use libc at all. And its size is a few hundred bytes smaller. Not as much as I was expecting. And let's take a look at this. So, the problem is that GCC doesn't really expect you to not need libc. Everybody needs libc, and so even though we're not actually using it, it's still linking it in. So we need to tell GCC to please stop doing that. Although at this point, we have to realize, of course, GCC is just simply calling out to other programs. It's just calling LD for us and passing in this monster command line that you can tell GCC to print out the command lines, and they're just horrible to look at. But we might actually be better off just calling LD ourselves at this point because we need so little of what is actually going on here. So we tell it we want a 32-bit ELF executable, and oh yeah, and we want stripping, I almost forgot. And then we just give it our object file. That should be a period, and didn't complain. And now the size is, whoa! Under 600 bytes by a significant margin. Significant. So, probably not going to get much smaller than that, but I mean, maybe we could. What's some other ways that we might be able to make it smaller? I'm thinking, let's take a look at the instructions that we've picked. So, if you know much about assembly, these are both 5-byte instructions. But now, EBX. I mean, we're only going to use the bottom 8 bits of EBX, so we don't actually have to use. So that's a 2-byte instruction there. And by the way, I just want to say, if you ever see anybody writing code in a modern time that tries to return a negative value from main, tell them please don't do that. Only the bottom 8 bytes are going to be used, so there's no point in passing that in. Plus, of course, most shells actually use the bit at 128 to indicate that actually a signal interrupted the program. So it's really frustrating if you don't keep your exit codes between 0 and 127. That's the end of the public service announcement. Okay, EAX, well, we're setting it to 1. So actually, even though this is a 5-byte instruction, but if we XOR it first, that's a 2-byte instruction. And then we can increment it. That's a 1-byte instruction. Increment happens to be one of those handful of 1-byte instructions left over from the good old days. So now we have cut out, let's see, it used to be 12, and now it's 2, 3, 4, 5, 6, 7. So that should save us 5 bytes, which, is something. It's worth counting. Did it work? Yes, it works. 228. That's actually 8 bytes. Well, the reason for that, of course, is that there's all this, padding that goes on there in the different structures and everything. Trying to keep it D-word light, we actually got a little bit of extra bytes out of it. So, well, although I don't want to sound ungrateful. I mean, look how far we've gone here, but I mean, it seems our program is 7 bytes long. We have 220 bytes of overhead. We're not linking with anything. What does readelf tell us? What is really going on? So you can see here .text, which is typically where your code goes, and it is in fact 7 bytes. So we know that part is under control. Section header string table, well, that's taking up about 17 bytes. Probably don't really care about it, but whatever. The point is that it's still 200 bytes. It doesn't appear anywhere on this table. What the heck's going on? Where are those 200 bytes coming from? I mean, it's amazing how fast we get used to things, isn't it? So anyway, unfortunately, to find this out, we really have to start diving in and find out what the heck an ELF file really looks like on the inside. That is also a huge subject, which I probably don't have time for, so I'm just going to kind of hit the highlights here of how it relates to us. An ELF file comes with lots of different pieces. There's a huge amount of stuff. A big chunk of it, as I mentioned, it has to do with dynamic linking. But there's all this other stuff. What's interesting about an ELF file is that the location of everything in it is not set in stone. It can be anywhere. There's only one piece of an ELF file that has a specific predetermined location, and that is the ELF header. And it has to be at the very top of the file. And it provides the directions for everything else. Actually, why don't I get us back to the top. So this is what the ELF header looks like as defined as a C struct. The type half is just simply a 2-byte value. Everything else here is just different kinds of 32-bit values. The 64-bit ELF actually looks very similar to this. Just anything that has to do with memory locations or offsets is just twice as wide. So the very first part is the ident section, which just it just has the magic number that identifies an ELF file plus some flags to indicate big endian, little endian before it dives into anything else. Then we've got some things here that just indicate the type of file, the platform it's for, etc. Entry is actually gives the memory location to jump to when the program begins. That's very important. That, of course, and that's the thing that the linker gets from the underscore start symbol and places there. Then we have the offset for the program segment header table and the offset for the section header table. And down here we have the number of entries in each of those tables and also some checks to make sure that we have the right sizes for them. And that's it. So the program segment header table and the section header table then give you the rest information. What those look like, let's take a look at the program segment header table entry. This is just one entry. We have a type, which indicates what kind it is. The most common type is marked value 1, which just means to be loaded into memory at runtime. We have the offset into the file where it's located and the size of the chunk in the file that's to be located. And then we have addresses and the memory sizes. And so this provides a mapping of one piece of the ELF file from the file to memory. There's some other things here about the flags give you the permissions to set on the memory and the alignment. It's pretty much very simple stuff. It just shows how the file on disk maps to the running program in memory. I'm sorry if I'm going really fast. Please feel free to interrupt me, by the way. If any of this needs clarification, I'm more than happy to.
I guess I have a question. How are you printing out those C headers? Does C some alias you have?
Yes.
Okay.
Yes, I tried to minimize the amount of typing I would hear so you wouldn't have to sit here and watch me fumble. So the section header is a little bit similar. It also has types and flags. It has the offsets into the file for chunks and the address where they'll be located, their sizes. Some extra information that kind of shows how they relate to each other and the kind of information that it contains. So one of the first things that most people think when they look at this, they say, okay, you've got your program segment header table, which gives you kind of a global map of everything in the ELF file. And you've got the section header table, which gives you this map of everything in the file. What the heck? Why is there two completely different maps for the exact same information? And it's a good question, and it's an important question. The section header table goes into more detail and gives you more information about how the different sections interrelate with each other. Several sections depend on information in other sections. The program segment header table gives you more information about how things look at runtime. The important thing is that these two maps are being used by two completely different types of programs. The section header table is used by programs that have to create, analyze, or modify ELF files. It's used by the compiler, the linker, it's used by readelf, it's used by the debugger. Almost anything that you can think of that mucks around with ELF files looks at the section header table. The program segment header table is specifically for use when a program is being run. It is used by the kernel, and it is used also by the dynamic linker when it's resolving symbols at runtime. So this is the reason for the two things. They serve two slightly different purposes. In particular, the program segment header table is absolutely essential if you actually want your program to run. The section header table is not used at all when your program is being run. So if we could find some way to get rid of this thing, we could make our file even smaller. But there's a problem. No program that creates ELF files is going to create it without the section header table because it needs a section header table. Nobody wants to know about a file that doesn't have a section header table. So we're on our own here. If we want to actually create an ELF file without a section header table, we are going to have to make it ourselves. Challenge accepted. Fortunately, we don't actually have to get out a hex editor and start doing it all by hand. A good assembler will allow us to still, define the file, still allow us to use things like, labels to do the calculation of memory locations and offsets and things for us. So that helps a little bit. I don't know if GNU Assembler really has those kinds of features. I'm sure it does, but I haven't looked at it. A lot of people use NASM, which is the NetWide assembler. It's a very popular free software. I recommend it. And of course, it has a bin file output that just simply takes whatever you give it and just dumps it straight out into a file. So I think that's what I want to look at now. So Here, I have assembled, after great effort on my part, of carefully reading the ELF standard, which of course I'm going to skip over because that would take forever. A empty, plain, executable, artisanally created by hand. For those of you who may not be familiar with an org instruction, that simply marks the origin, shows where everything is going to be, it assumes where everything is going to be loaded into memory. This number looks kind of random, but it's just simply the default number that Linux uses for 32-bit ELF files. It doesn't actually have to be this value, but it is the one that is used by default. Here is our ident section. Here's our magic number that indicates this is an ELF file. It's little endian, 32-bit, version 1 sort of thing. Type, it's an executable. In case you didn't know, there are actually four types of ELF files. Object files. Your object files are ELF files. They look a lot like your executables, actually, if they're simple enough. Executables, dynamic libraries, and core files. 3 indicates that it's a 32-bit x86 platform. Version, there's only one version, r_start, that refers to a symbol down below, which we'll get to. And then this is calculating the offset to the program segment header table. Since we don't have a section header table, this is 0. No flags, header size, blah, blah, blah. One entry in the program section header table. And now we'll scroll down, and here we have our program segment header table of one entry, one item. Begins at offset 0 and includes the entire file. That's pretty standard. Any program that runs just to keep everything page aligned is going to load the entire file. Not the entire file, but starting from the beginning. It doesn't work if you can't just simply mmap a file to execute it. So everything needs to, alignment considerations are very important for this stuff. So whenever you run a program, it's ELF headers in memory, even though it's not actually being used for anything. This symbol, $, just simply is the origin value. So that's our address we're loading to. File size is defined down here. There's our permission bits. The permission bits are the same as they are for LS chmod permission bits. 4 is readable, 2 is writable, 1 is executable. So we mark our memory to be readable and executable. Page alignment, and then we can just stick whatever we like in there, and this should just work. So let's take a look at that. Let's just go down here and let's see, how does that go again? Let's see, EAX, EAX. No percent signs now that we're no longer using gas. And I think NASM bin output to foo. Yes. And now the size. 91 bytes. 91 bytes. You know, I really like this program. One of the reasons I like it is that this is the first program we've looked at where we actually know everything that's in it. We actually intentionally picked everything that went into this file. We know why it's there and why it needs to be there. So this is perhaps the smallest we can get. Or it's not fair to spring this on you, of course, because you didn't read the ELF standard, but I did. And one of the things I noticed early on is that it mentioned that not only can all the different pieces of an ELF file be anywhere in the file except for the ELF header, they're actually permitted to overlap. Our program is only 7 bytes long. And I couldn't help noticing that, right at the top of the file, there's all these zeros. They're just padding, just in case a later version of the ELF, standard needs them. I don't think this should actually be a problem. I mean, a later version of the ELF standard, would probably complain about finding a bunch of random numbers there, but, that's probably not until a long time, maybe never in the future. So I think this ought to work, Let's take a look. Okay, so now our executable is exactly the size of one ELF header and one program segment header table entries. So now we have gone as far as we can go. I mean, unless, of course, we could do with the program segment header what we just did with the program and actually stick it inside the ELF header. But I mean, well, maybe not all of it, but maybe part of it. We can, let's see, like, okay, well, so these 8 bytes here and these 8 bytes here kind of look similar to each other. In fact, they kind of look like they might be identical to each other. So now we're just overlapping stuff. The ELF standard says that you can do that, right? Okay, so I think now we've gone as far as we can go. Well, I mean, obviously, if we could just get a little bit higher, then we could do even better. But we've got these numbers over here that don't really match up. It doesn't really look like it's going to work. I mean, unless we could change some of the numbers so they did match up. I mean, is like this number here. I mean, this is like the size of the program segment entry, the program segment header table entry. But I mean, Linux should already know what that value is. It shouldn't need to have it. I mean, is it actually checking? I mean, what if we just changed it to some terrible, ridiculous number? Would it complain? Yeah, okay, yeah. Okay, so that one didn't work, but if you spend some time playing around with these things, eventually you will discover there are quite a number of values that aren't being checked. So after doing this, I found, so the red ones indicate ones that are actually being used by the loader and actually really need to have values. The entry, you gotta give the address of where you're gonna run the program. That obviously, you have to tell it where the program segment header table is. And then like these purple ones here, like the version, there's only one version of the ELF header, so it's not at all surprising that Linux isn't even bothering to look at it. Anything having to do with the section header table, it doesn't care about the section header table. If those are garbage values, it won't even notice. The ident, of course, you've got to have the measure number at the beginning, but the numbers after that, well, if they don't make sense, Linux just says, oh, whatever, it's just fine. So you can kind of get away with some pretty terrible stuff in there. And now, let's take a look at the program segment header table. That one's a lot less flexible. Almost all this stuff is being used. The one main thing is like the V adder and the P adder, which is virtual and physical. The executables don't have anything to do with physical addresses versus virtual, so the adder is the one that's actually used. Flags, of course, the bottom 3 bits are very important, but that still leaves 29 other bits that aren't really being looked at. So, there could probably be something there. Alignment. Linux doesn't care about alignment at all. That stuff is for, other people back when they were still creating things. So after poking around and looking at this stuff a little bit more, I managed to pull together something a little bit more mixed in with itself. So this requires a little bit of obnoxiousness, but you can see we've got this great bit here where there's a whole bunch of important stuff in the program segment header table, which lands right there, a bunch of stuff that's not being used by the ELF header. So we get away with it. This breaks down a little bit when we get down here, the program header entry size, which I showed you. Linux does not like to have it wrong. That happens to, kind of land in the same place as half of the address of where we're actually supposed to load our stuff. That makes a problem. So the solution to that, of course, is, well, yeah, we change where we're loading. There's a fair bit of leeway. As long as the bottom half is all zeros, you can use just, and the top, and the number itself is a negative, you can actually use quite a bit there. So that allows us to get away with doing that, and then everything else just kind of more or less lines up perfectly. And so we've now got a huge chunk, only we have like just the last 3 fields sticking out of the bottom. And let's see, did I do this correctly? Does it work? Does it work? Does it work? Does it work? It works! 64 bytes, okay. Well, presumably that's as low as we can go, but obviously, if we could get the entire thing, if we can get the entire program segment header table inside the ELF header, then that's like the holy grail, right? Can we do that? Can we do that? Well, after looking at it for a while, these numbers, I mean, you just can't push this up another, 8 or 12 bytes. It's just, it will not go at all. There's too much important stuff right here. The other alternative would be to try to move the program segment header table up. If we stuck it up here right after the magic number, that gives us 12 bytes to store a bunch of stuff. But then right after that, we hit all kinds of problems. And of course, that's where our program is currently located. So it looks kind of bad. We may have some problems making this work if everything worked the way that it was documented to work. However, if we play around with things a little bit, we can create this rather horrible thing. The flags that give the permissions for the memory, as I mentioned, there's readable, writable, and executable. Obviously, we need to have the executable bit set. You would think. However, as it turns out, Intel memory paging does not have a concept of executable versus non-executable memory. There's only read-only memory and read-write memory. So the readable bit and the executable bit are actually redundant. If either one is set, it's marked as readable. So we can set that value to 4, and it will still be executable. And you'll notice that if we set that value to 4, 4 happens to be the offset of the program segment header table where we're sticking it in our new location. So by putting it all the way up here, we can get this in here, and then this 4, even though it is used in both places, will work in both places. Now, unfortunately, this means that the file size, or I'm sorry, the memory size lands on the same place as the entry, the address where the code actually begins. So we have to set this _start, which is kind of bad. But, I mean, it just means that we're asking for more memory than we're actually going to use. That's not illegal. That's perfectly fine. So yeah, so we can get away with that. It does, however, cause something else that is a little bit weird that probably needs to be explained, is that I have to set the file size to _start as well, which is ridiculous, because this is a huge number, and not at all the size of the file. Why in the world would I do that? The problem is that if the file size is actually smaller than the memory size, but you don't have the writable bit set, then you're going to get a seg fault when the program runs and it tries to zero out all the memory beyond your file size. So if you tell it the file size is the same as the memory size, even though the file size you're giving it is way, way bigger than the file's actual size, Linux won't try to zero out those bytes, and it won't complain about the fact that this is read-only memory. I feel a little bad, like I've been caught lying to somebody here, but I can't let that stop me. So, what the heck? So, this monstrosity actually builds, and now we have an executable that is the size of an ELF header. We are down to the bare limit. There is no further we can go. I mean, you've got to have an ELF header just to get loaded, right? Right?
So.
Turns out we have one last dirty trick to pull out of our sleeve. It turns out that if you give it a file that doesn't even have a complete ELF header in it, Linux will still attempt to go along, and it will simply pad out the remaining bytes with zeros. There are 7 bytes of zeros at the end of our file. And if we remove them, amazingly enough, we have a working executable. Now, we have truly gone as far as we can go. There is no getting around the fact that the 45th byte, which contains the first byte of the number of entries in the program segment entry table, needs to be non-zero, it needs to be present, and it needs to be 45 bytes away from the beginning. Ladies and gentlemen, the world's smallest Linux ELF executable. Now, when I've shown this to people over the years, and one of the reactions that I got was somebody telling me, well, you haven't really created the smallest Linux ELF executable. you've created a 45-byte file that the current version of the Linux kernel mistakes for an ELF executable. It's a fair point. So, not that I'm ever going to give this up, but, just, out of curiosity, it made me wonder, okay, well, then what is the smallest executable I can make? So we went off the straight and narrow, of course, is when we jumped away from our original thing. We started putting stuff inside of things that it wasn't necessarily supposed to be in. However, that doesn't mean that we don't have any tricks at all that we can't still use. And so I went around and kind of poked around a bit on this and found that I could still improve things a little bit. We can still do the overlapping of the first 8 bytes program segment header table with the last 8 bytes the ELF header. That is still perfectly acceptable. All these bytes still have to be 0, though. Yeah, the ELF standard is pretty clear. Whenever you're using a field that doesn't actually being used by your platform, it should be set to 0 almost every single time. In fact, close reading of the ELF standard, I found only one place where it varied from that, and that is the p-adder field. And there it specifically says that the Intel platform does not use it, and it should be ignored by implementations. I take that to mean I can put whatever I want there, and it'll still be okay. So, if I can squeeze now my program to fit in there, well, I can't. I mean, we've got, how many bytes here? 7 bytes. That's not going to fit in a 4-byte field. However, the one just before it is our address. So again, by being a little creative about what our address is, this is the encoding of initializing the BL register with 42. So the first instruction actually overlaps with the memory location that it's loading to. We can get XOR and increment, so we get our registers done, but unfortunately that leaves us only 1 byte left in the p-adder field. After that comes the file size field, which we can't really mess with. The mem size field, we have some leeway with. Obviously, it's completely legal to have a bigger one, but we have this file size in between. And unfortunately, a jump takes 2 bytes, and we only have 1 byte left. So the way around that, well, as you can maybe see, anyone have any idea what's going on here? This random byte? This random byte is the encoding of the instruction that compares EAX with a literal value. So it sets the flags and doesn't do anything else. So these 2 lines are actually a single assembly language instruction. So this is a way that you can kind of use 1 byte to jump over a 4-byte field. So it's a little messy, but this all works. Or I should say it all works. I assume it all works. And it does. So 76 is the smallest I've been able to get a program that completely adheres to the ELF standard and the Linux API. Well, except, of course, for the fact that I'm actually making a system call manually. The system call numbers are not part of the ELF ABI. Is anybody here unfamiliar with the term ABI? Yeah, ABI is short for Application Binary Interface as opposed to an API. So Unix has an ABI as well that shows how programs are supposed to behave when, actually is executables and how they're supposed to set up. An ABI shows what registers are actually being used so that programs that are compiled with different compilers can still call each other correct and everything works correctly. So the ABI has nothing to say about what the numbers are for the various system calls. And in fact, 64-bit Linux uses a completely different set of numbers as well as a completely different way of calling them. So, I mean, it's unlikely that the 32-bit Linux is ever going to change, but if you wanted to get really technical and say that you have to completely adhere to all standards, the smallest ELF would actually then have to do dynamic linking. And all of that machinery that I just tried to ignore earlier has to get brought back in, and it is a huge, huge mess. I have played around with it because, I mean, how could I not? But it is not a small thing. There is a huge amount of so here's this is the dynamic section. This just has, it's kind of a grab bag of information that a dynamic linker will need while running. And it basically shows location and size of all these other sections, as well as the names of the libraries that actually have to get loaded in We have up here our string table that actually lists the strings that we need, and our underscore exit function, since we're going back to using that. And of course, the name of the library that it's located in. We've got, this is the program that actually is invoked to do the dynamic linking at runtime. Our relocation table shows us where the address of these functions actually has to get stored in the running program. Our symbol table entry connects up the strings with the relocation table. Oh my God, it just goes on and on. And then, of course, we have a hash table because, you know, dynamic linking is kind of a big deal. And you have to have a hash table to try to speed things up. I have written here the smallest possible hash table I could make because I don't care how long it takes. I'm just trying to run a program. And I still managed to squeeze the actual program itself, ran up here into the dynamic table. A little bit more. I still had to do a bunch of jumping around to get it all to work out, but you know, it mostly works out. But yeah, it's a huge, huge, huge program. Does it still work? It does still work. And it is 301 bytes. I haven't given up. I still hope someday make it smaller. But that's where I am currently with that one. Somebody wanted to ask me how small I could get one that was using a 64-bit ELF. I managed to get that one down to 84 bytes. That one, I really have no idea. Linux is a lot more demanding about the 64-bit one. It has a lot fewer fields that it will politely ignore if they're filled with garbage values. The version that you see here, this is actually, oh God, this is so ugly. So even though a lot of these things are now 8 bytes, 64 bits wide, a lot of these fields, the only way I could get this down below 100 bytes at all was I've got the program segment header table actually not 64-bit aligned. It's 32-bit aligned, but the program segment header table actually begins halfway into the E entry fields. I don't know how that worked, but anyway, it's down to 86 bytes. Of course, none of these programs actually do much of anything. If I want to know about a program that actually does something visible, it takes a little bit more, you know? So somebody, I just naturally, okay, well, how about Hello World? How big can Hello World get? I played around with it. Runs, and its size is 62 bytes. Pretty good, not bad, considering that I've got a 13-byte string crammed into it. Completely not at all according to any kind of standard. So we've got all this stuff. We have another case where we're actually like running code that passes through a field that has to be set. So now not only is the program setter offset pointing to the beginning there, that 4 also being the read-only value, that 4 also happens to be the system call number for the right system call. So this is not actually just jumping past it. We're actually initializing EAX to 4 at this spot. So now, I love it. This value actually has 3 purposes now. So yeah, so that works. That works pretty cool. I have not been able to get any smaller than this. However, I have to share this one program. I didn't write it. It no longer works. It worked briefly for a while with certain 2.6 kernels, I believe, and now it stopped working. But it is absolutely amazing. I don't actually know for sure the name of the person who wrote it. It was on a Japanese website. I think the author's name is Kikuyan, but it's not really clear from the way the website is set up. And this person did something absolutely horrible. And I can't believe they got away with it. So one of the things you notice when you look at like, okay, well, can I just have some of these values just be treated as instructions and just execute past them? One of the things you note is that small integer values tend to map to Intel instructions that read and write memory. Because all of the registers are initialized to 0 when your process starts, you can't really do anything like that until you've initialized those values. And so almost all of the instructions that only involve register-to-register work all tend to start with values that are 192 or higher. But what this person did, you see the start? These 3 instructions, by the way, are 1-byte instructions that map to capital E, capital L, capital F. The program is actually starting at position 1. which they had to do because they've got position 1 actually overlapping something else in its. But then immediately after that, we've got all these things that start accessing memory, and when the accumulator hasn't really been initialized with an invalid value, what they did was they loaded their program at location 0. Location 0 suddenly becomes valid writable memory, and all these instructions work. They don't do anything useful, but the point is that you don't have to jump over them. So you can start at position 1 and just ignore all these instructions, and every time you hit a spot where you can change the value, you just squeeze in another instruction. And by the time you get all the way down to here, you have, ta-da, enough code to actually output hello world. It no longer works, so I can't actually show you running it. I don't think it's ever going to work again. But it was, how big is it? 57 bytes. And I don't think I'm ever going to touch that. How are we doing on time? We've got a few minutes. Is there any questions? Anybody?
What are the binary formats does Linux support?
Oh, that is actually a good question. By default, almost everything I look at pretty much supports ELF, nothing else. Back in the day, it used to be pretty common that Linux would come with 2 executable file formats, ELF and the AOUT file format. In fact, way early Linux, like 0.9, AOUT was the only thing it supported. AOUT does not support dynamic linking, and so that's why they moved to include ELF. But so for a long time, AOUT was still included with most things. If you build a kernel with AOUT support, you can get a much smaller program. It doesn't, because the AOUT header only has like 8 fields, and I think one of them can be messed with. I actually don't have that in my notes. But yeah, I actually do know the number. And it is smaller than 45, but good luck finding a distribution these days that still supports AOUT out of the box. And of course, you could, in theory, write your own kernel extensions to create new executable file formats to get even smaller, if you were willing to go that route. Anyone else?
So for my own curiosity, can you open up that 57-byte file in a hex editor just for
Sure. I'm not sure I have a hex editor on this machine, but I can certainly show it to you here. And of course, we can also use Emacs, which actually, yeah. Hexel mode. So yeah, unfortunately, there's not much to look at. You can see ELF and you can see hello world. Everything else is just invalid values. But exclamation point, that is 21 hexadecimal. That is, I don't actually know what that is. It's at that point in the code, it is an instruction. I'm pretty sure. Oh, no, I know what that is. You'll notice that we only have O comma world here. Unfortunately, the last 4 bytes, this is actually the end of like part of the program segment header table. So what this person did was they actually copied the HELL onto that spot while the program's running. So, because once you're in memory, it doesn't care if your program segment header table is now bollocks. So, ta-da! Anyone else? All right. Thank you so much for coming.